All right, today we're learning a new proof technique. Today we're going to talk about the contrapositive. And as you can see, I already have this right now, what we're going to do. It's pretty direct. What we're going to do is assume not B and show that this implies not A. So what I'm saying is if we have a statement of the form like if A, then B, it's logically equivalent to prove if not B, then not A. If you don't believe me, I'm going to do a little truth table, right? Truth tables are something we did when we started learning Boolean algebra. So if what I'm about to do does not make any sense to you, I already have a video about Boolean algebra. Maybe I can make it like pop up on screen right now, and you should really watch that. Because if you don't understand what I'm doing right now, then I don't think the rest of this video is going to make too much sense to you. But anyway, if you do know what I'm talking about with truth tables, then hopefully this proof technique will make sense to you. So let's go through and construct this truth table. So we're going to start by assigning values to A and B. So true, false. Oh man, I can't speak. True, true. True, false. False, true. And false, false. So then A then B will have true, false, true, and true. For not B, we have false, true. And for not A, we have false, false, true, true. And then for not B implies not A, then we have false then false is true, true then false is false, false then true is true, and true then true is true. So as we can see on the truth table, the values for A then B and not B then A are exactly the same. Therefore, they are logically equivalent. Therefore, showing one is equivalent to showing the other. And in some cases, showing not B implies not A can be way easier than showing that A implies B. Now, if you still can't see that these are logically equivalent, I mean, you can see it, obviously, I just wrote it out, but if you're having a hard time believing it, let's do a little example, right? Like a real life non-math example, right? So let's say I have the statement, if I go to the store, I will get oranges, right? That is our very basic example. So in this case, A is our premises, B is our conclusion, right? And yeah, if I go to the store, I will get oranges. So A then B. And what we want to show is that this is equivalent to not B, then not A. So let's think about not B for a second. All right, I did not get oranges. Therefore, I did not go to the store. And that should make sense, right? Think about it. I didn't get oranges, right? Well, we know that if I went to the store, I 100% am coming back home with some oranges. So if I did not go to the store, then, if I did not get oranges, then there's no way I went to the store. Because if I did go to the store, I'd have some oranges. Does that make sense? I really hope that makes sense, and I'm not just talking about oranges for no reason. Anyway, now what we're gonna do is actually apply this to math, right? I'm gonna make a claim, and it's gonna be a whole lot easier to show with the contrapositive, right? So here's what my claim is. Claim. So I claim, let R be an equivalence relation. Remember when we talked about those? I don't know how long it's been. Let R be an equivalence relation on a set A. And let A and B be elements of A. I'm going to say if A does not relate to B, then their respective equivalence classes, the intersection between them, is the empty set, right? And this should make sense. This is something we talked about. We said that with an equivalence relation, if A relates to B, then they belong to the same equivalence class, which means that their intersection would not be empty. So now what I'm saying now is that if two elements do not relate to each other, then the intersection between their equivalence classes is empty, right? Because their equivalence classes are disjoint. So if A does not relate to B, they're in disjoint equivalence classes, so their intersection would be empty, right? This is harder to prove going the direct way. You could try it, right? So what I'm going to do is show it with the contrapositive, right? Which means I want to show here. I want to show, and here, let's label these A then B, right? So this is our premises A, this is B. I'm going to negate B and hopefully reach not A. And if I could do that, then that means A then B holds, which is what I want to show. So let's do our proof, right? proof. And you're going to see this is super easy. Now I'm going to start by letting the reader know what kind of proof technique we're using. So we will do a proof by contrapositive. So now the reader knows, okay, he's going to assume, or whoever it is going to assume not B. I'm going to be on the lookout for them reaching not A. If they can do that, then I know that the statement, if A, then B holds. So we will do a proof by contrapositive. So suppose A's equivalence class intersect B's equivalence class is not the empty set, right? So we negated B. So we're supposing that their intersection is not empty, therefore there's an element in it, right? So then there exists some x, right? Let's say some x in A such that x relates to little a and x relates to little b, right? Okay, cool. Now R's in equivalence relation, right? So then by reflexivity, or sorry, not reflexivity, then by symmetry, A relates to X. And by transitivity, A relates to X and X relates to B implies A relates to B. Now, remember, my premise is A, where A does not relate to B. Since we're doing a proof by contrapositive, I want to show not A, which means I want to show that A relates to B. And look at that. In 2 sentences, well, I guess 3, or 4, I showed not A. I showed that little a relates to little b. And that's it. That's literally it. My proof by contrapositive is done. I suppose not B. I showed not A. And since we know that that is equivalent to showing if A then B, then I've shown what I wanted to show. And that's it. That's the end of our proof. And I mean, that's it. This may seem like a little anticlimactic, but that's all there is to say. There's the proof by contrapositive. So if you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.